Hi folks, we're going to take a look at number 12 from page 146, and what they want us to determine is the area of the largest rectangle that can be inscribed in a right angle triangle with legs 5 centimeters and 12 centimeters. Okay, so the legs are the two sides that are not the hypotenuse. Okay, so essentially we've got this triangle here, okay, legs 5 and 12. Could have drawn it the other way with 12 and 5, wouldn't make a difference. And I need to inscribe a rectangle in there, and it tells me that two of the sides have to lie along those two legs. Okay? Now, what we'd like to do is solve this problem using calculus. So if we want to solve this problem using calculus, we need a function to represent the area of this rectangle. So what I'm going to do is I'm going to take this geometry problem and turn it into an analytic geometry problem. And I do that by placing this triangle on the Cartesian plane. Okay, so let's do that here. So I've got my Cartesian plane here. So let's say I pick along the y-axis as being the smaller side. Okay, so I've got one length along here with a height of 5, and I'll use the x-axis for the other side. Okay, so there we go. And so the hypotenuse, or the function that I'm going to work with, okay, is just given by that line. Okay, so what I want to do now is I want to inscribe my rectangle in here, and I see that if I want to find a formula for the area, which is the length times the width, well, I can easily use whatever x value I get to along the length of this rectangle and call that x, since it's along the x-axis. Okay, and this is when I realize that the width of this rectangle is just going to be the y value of that line at the given x value. Okay, so that means we need to determine the equation of this line. That's pretty easy. Okay, so what's the slope of this line? Well, it's just rise over run. So my run would be 12, my rise would be -5. So -5 over 12, and of course my y-intercept is just 5. And so the equation of this line is just -5 over 12x plus 5. Okay, and there we go. So now I can come up with an equation for my area. Okay, so the area is just length times width, so the length is just given by x, and the width is just given by the y value of that line, which is -5 over 12x plus 5. Okay, so in other words, the area is given by -5 over 12x squared plus 5x. Okay, now it does make sense that I'm looking for a maximal area since my leading coefficient is negative. Okay, so you could obviously solve this by taking the derivative and determining where the x-intercept is of the derivative function. Okay, but if you watched a previous video, you'll see there's a neat little trick for finding the location of extrema on quadratics. Okay, so here we know that that's going to occur, okay, at the value b over 2a. Sorry, negative b over 2a. So it's going to occur at -5 divided by 2 times -5 over 12. Okay, so let's take a look at what that gives us. So the negatives cancel out. Okay, so here I can think of this as 5 over 2. Okay, and since I'm dividing by 5 over 12, that's like multiplying by 12 over 5. Okay, and so here 5 and 5 cancels out, so that occurs when x is equal to 6. Okay, now something that's interesting here, okay, is notice that 6 happens to be exactly halfway between 0 and 12. Okay, so halfway along that lower leg. Now even though, so they're actually asking me for the maximum area. Okay, so we can calculate that here without determining the height. So let's do that. So, you know, area is equal to -5 over 12 times 6 squared, so that's 36, plus 5 times 6. Okay, so here, what do we have? 36 over 12 is 3, so -15 plus 30 is just equal to 15 centimeters squared. Okay, So now we already saw that x happened to be exactly between 0 and 12. Okay, so 15 centimeters squared. Well, is there anything interesting about that? Well, what's the actual area of the original rectangle? Okay, well, 1/2 base times height. So 1/2 times 5 times 12, which is 60, is 30. So we see that the area of the rectangle, the largest one that we can inscribe, is exactly half the area of the original triangle. Okay, and we see that the length of the rectangle is exactly half the length of the triangle. So it'd be interesting to see if there's any connection with the height. Okay, so let's determine the width of that triangle. Okay, so that's -5/12 times 6 plus 5. Remember, that's what the width of the rectangle was given by. And so here that becomes 2. And we have -5/2 plus 5, which is just, well, 5/2. Hey, exactly half. Okay, now it could be that this is just a coincidence. Okay, or maybe there's something interesting going on. Maybe there's a pattern going on. So they ask us to redo this for a right triangle that has sides 8 and 15 centimeters. But just to make it a little more interesting, I'm going to redo this problem in a much more general way. Instead of using another specific example, since in part C they're asking me to make a conjecture about these patterns, I might as well see if I can prove the pattern. Okay, so what I'm going to do is I'm going to work with any old length of legs. So instead of calling this a particular number, I'll just call this A, and I call this B. Okay, and I create my triangle, and I'm inscribing a rectangle in there. Okay, so let's see if we get to the exact same patterns. Okay, so if we look at the slope of this line, well, it's just, again, run of B, rise of -A. So it's just -A/B. Okay, the y-intercept is just a, so the function here is just given by -A/bx plus a. Okay, so again, do the same thing. I'll call the length of this rectangle x, and so the width of the rectangle is just going to be given by the y value of that function at x. Okay, so let's come up with an area function. So it's just going to be x times -A/bx plus a. So my area is given by -A/bx squared plus ax. Okay, so again, you could just take the derivative and solve for the derivative being equal to 0, or you could use the fact that the critical point is given by -b/2a. So -b, so the coefficient of x is just -a/2 times the coefficient of x squared, so -A/b. Okay, and if we fiddle around with this, this is -A/2, okay, times -b/a. Since we're dividing by a/b, it just becomes times b/a. Negatives cancel out, the a's cancel out, and lo and behold, what do we have? b/2. So that means the x value, which is going to give us the largest rectangle, is exactly half the length of b. Okay, let's see if we get exactly half the length of a. Okay, so let's calculate that y value. So -A/b times b/2 plus a. B's cancel out, so -A/2 plus a is just equal to a/2. Okay, so the height of this rectangle is going to be exactly half the height of the triangle. And now let's see if the area is going to be half. So the area of the triangle, okay, is just equal to, well, a times b divided by 2. So let's now find the area of the rectangle. Okay, so the area of the rectangle is just, well, the length times the width, so b/2 times a/2, which is just equal to ab/4, which is exactly half the area of the original triangle. Okay, so this not only gives us a conjecture as to the result when we're maximizing the area of a rectangle inscribed in a right angle triangle, it actually proves it. Okay, so that rectangle will be exactly half the area of the triangle, okay, and its dimensions will be exactly half those the dimensions